Hi everyone, today's video is gonna be a bit long because we have a lot of stuff to work on, and essentially we are gonna dive straight into the fundamental theorem from my perspective, again fundamental, for all of the deep learning thing, because by the end of this video we're gonna understand entirely and mathematically why exactly neural networks work and how they know stuff, because with such videos I want to bring you the understanding, and I want to bring some understanding for me of how, and the most essentially why do most of the deep learning concepts work. For example, CNNs, I think you don't specifically need to know how they work, but mathematically they are not really complicated. And again, neural networks are mathematically not really complicated, but the thing comes is that how do some sort of a weighted sum of some nonlinear functions can understand that your face is your face, who Michael Jackson is, and all of this stuff, and how does exactly, for example, ChatGPT knows how to, I don't know, to solve an equation, because I think it has never seen it before, and that's the interesting thing. So, as you may know, we are gonna dive in straight to this not really big paper, I think, but I think it's really interesting because, no lie, I was once reading this one, and but I wasn't really engaged in the process, so I just wanted to understand by intuition. So today, me, without knowledge about this, I know this math basically, but I didn't essentially dig deep in this stuff before. So we're gonna work only today with this paper on LaTeX. I don't know why. I think it's not probably gonna be needed. This writing tool from Figma, I think it's convenient to use if we need to show something. Yeah. A bit of Google, a bit of Desmos, so on equal 6, we can basically show interesting things here. So yeah, I think let's dive in. This paper is from 1989, just let's imagine that it's really old, called Approximation by Superpositions of a Sigmoidal Function. What essentially is a sigmoidal function, we don't really care, but for the sake of being interested, so it's like 1 divided by, as I remember, 1 plus exponent to negative x. Yeah, so as you may see, as x goes to the infinity, we're essentially getting like 1, and as x goes to negative infinity, we go to 0. But in terms of this, I think it works like that. Just a function that squashes x between two numbers, essentially. Firstly, reading abstract, yeah, I think we need that in this paper. We demonstrate that finite linear combinations of compositions of fixed and varied function and a set of affine functionals can uniformly approximate any continuous function of n-real variables with the support in the unit hypercube. Alright, we're demonstrating that a linear combination of compositions of fixed and varied function. So we are looking for the composition of a varied function, something like weighted sum probably. And a set of offline functionals. What are the offline functionals? Again, I think we're allowed to use Google. Translation, scaling, reflection, rotation. So we are just doing things like multiplying it by a number. Well, makes sense. Can uniformly approximate any continuous function of n-real variables with the support in the unit hypercube. Alright, so we're basically stating that Okay, like we can take a certain function, do some non-essential stuff with it, like multiply it by a number, squash it, do whatever we want, but keep it as a function itself. Add some other variations of this function, maybe with different variables or something like that, with different weighted sums. And by that we can approximate any continuous function. And what I mean by approximate is that essentially, I think I might give a cool example. For example, we have this kind of function, and what we only care of is that, like, this field. So we don't care that it goes down here and it goes again and again. What we only care is the distance between essentially 0 and 1. And so what we want to create is a function that looks similar to this like point. And what we want to do is that we may create a simple function like x equals y that is, I think, almost similar like here. And why it's relatively easy, it can work on this certain on this certain distance as the function that is sinus x. So yeah, we're approximating, we're finding the function that is much easier than the initial, but it on some distance it's just similar to the initial function, so it can work just like that. So again, what we're essentially saying is that this just treated like a combination without those fancy effluent functionals, is that we can mimic any existing function with this combination of some compositions of a fixed and varied function. Okay, like it makes sense. Only mild conditions are imposed on the unvaried function. What does it exactly mean? Unvaried function, what is that? Yeah. What is that? Varied. Dang. Sorry. Object is an expression function of polynomial involving only one variable. Yeah, so we have only one independent variable here. So only mild conditions are imposed on the unvariable function. What does it mean? Well, I just look like that. Yeah. Mild conditions means that the function does not really satisfy. Oh yeah, okay, I get that. So what we're saying is that we're approximating, but it's essentially never the same. So of course sin x and x equals y look extremely similar here. Essentially they are like relatively similar. They're not entirely similar, there is still the difference, but if we look like that, there is like no difference at all. Alright, yeah, it makes sense. Our results settle an open question about the representability in the class of single hidden layer neural networks. Yeah, so yeah, that's the easiest of the year, essentially doing all of this stuff to implement it in one layer neural network. And by the way, just from my perspective, one layer neural network is essentially what they are talking about. It implies that the combination of whatever functions. In particular, we showed that the arbitrary decision regions can be arbitrarily well approximated. Yeah, that's what I was talking about. So again, this from like 0 to 0.5, it's better. So like they can be approximated some regions. Can be arbitrarily well approximated by continuous feed-forward neural networks with only single internal. Yeah, that's in terms of, if you don't know. Yeah, in terms of if you don't know what is one layered neural network. Yeah. So what is a neural network? Those are all like inputs. You have some variables, you pass them here. Each variable is passed to every kind of neuron. This neuron has a certain function. In terms of this paper, it's sigmoid, just as I have presented here. And instead of x, we're using the weighted sum. So it just does something with all the inputs and gives it to the output. So essentially, one layered neural network can be seen again as the combination of our sigmoids. So yeah, and then you continuous sigmoidal nonlinearity, and this is about the function itself. So we cannot just say that our function must be f from x equals 5x. It's not nonlinear. Sorry, it's not nonlinearity, and this feature is essential because what we're stating here is that do we have max function 1x? Yeah. If we have this function, its nonlinearity it's nonlinear. We cannot represent it as like 5x plus 7y plus I don't know whatever it is. So this is a linear function, because if each neuron has something like 5x, like 6x, 1x, like 11, like that's x, 15x. So this is a linearity actually. And if it's linearity, we may just not use all of the different neurons. We can just write whatever that is: 5 plus 6, 11, 12, 12 plus 15, 27x. It's just the same thing essentially as the sum of all of those things. But we cannot do with those kinds of functions because those are nonlinear, and when we have something like 13x, we cannot just say that essentially if we sum them up is the same as maximum from like 1 and 14x. That's it. That's the whole point. So yeah, we're looking for nonlinearity. The paper discusses approximation properties of other possible types of nonlinearities that might be implemented by artificial neural networks. It's related to the statement that we're using the sigmoidal nonlinearity, which I have shown you here, is called the ReLU nonlinearity. Again, I'm sorry. So we're just squashing all of the values that are like lower than 0. We're squashing them to 0, so it's non-linear function, but they are talking about the sigmoids, which I have shown you in the beginning of the video essentially. The paper discusses approximation properties of other possible types of nonlinearities that might be implemented by artificial neural networks. Again, just implemented by neural networks. Yeah, keywords are really fancy. Neural network, approximation, completeness. Never seen completeness here, but whatever. Alright, let's dive to the introduction itself, and it's gonna be really, it's not really big. So I think at this video we're gonna discuss the introduction and do another one. I'm gonna record the main results because I don't know. I think the video shouldn't be like 2 to 3 hours long. Alright, a number of diverse application areas are concerned with the representation of general functions of an n-dimensional real variable x, which is n-dimensional, by finite linear combinations of... Yeah, bro is just restating this stuff like a million times, that we are concerned with this weighted sum of sigmoids. This is a sigmoid which I was talking about. And bro is just concerned to state that yeah, we're using a lot of sigmoids, a weighted sum of them, to represent general function. Yeah, and a bit of math here is that this sigmoid is not the same as just a weighted sum of them, because we are using matrices here. So you shouldn't really bother yourself with this fancy thing like y transposed x. It's just essentially a lot of x's multiplied by a lot of y's. So just weighted sum of a lot of x's, because we might have more than just one input variable, more than one number for input. And this is the bias. Again, it's the same matrix, we just added up. Alright, yeah, those are obviously fixed, because only the x is the thing that we tweak, basically, yeah. Why is the transpose so y? So is the inner product of, yeah, again, what I'm sorry, what I just said. Here the unvaried function sigmoid, I'm gonna call it sigmoid because he's giving it sigmoid properties, depends heavily on the context of the application. So this sigmoid is not essentially a sigmoid. Our major concern is what so-called sigmoids is that, yeah, just it may look really fancy, but again, just what I've written in the beginning of the video, 1 plus exponent minus x, it has literally the same properties. I'm gonna use this like here. Yeah, it literally has the same properties. So it's 1 as t in our terms x is gonna go to the plus infinity, and 0 is it's gonna go to negative infinity. You may just see it here, like, yeah, it's really small. It's like it's 0. It just says that it's 0, but obviously it's not entirely 0, but it's, yeah, you understand that, I think. Such functions arise naturally in neural network theory as the activation function of a neural node. Yeah, just as we were talking about. It's called a node. A unit is becoming whatever. The main result of this paper is a demonstration of the fact that the sums of the form 1, this one, neural network, are dense in the space of continuous functions on the unit cube if sigmoid is any continuous sigmoidal function. Well, like, I've encountered one time in my life. How is it called again? Unit cube, like unit cube of functions. It's gonna be hard to represent that, but yeah, like this one. Just imagine it this way. That's why I've prepared Figma. You have a certain cube. It's not entirely 3D. By 3D I mean it's 3-dimensional. It has height, like depth, width, whatever. It's a cube. Just a cube in a space like that. Yeah. But the thing is, let's say we have certain function like this one. It's y equals x, and another one y equals 5x, sinus x, cosine, cosines, whatever, tangents, all of the existing functions are in this cube. So everything you can imagine is in this cube, and dense in this cube. What it means? It means that our do you remember one layered neural network, or a combination, whatever you call it, is that it can basically be in all of the near all of the places in this cube. It's everywhere. It's literally everywhere. We can get close to any function. This is what means it's dense. So when we are essentially stating that it's dense in this space, just if you don't understand what I said before, just forget about it. Just imagine just keep on what I'm talking about. This cube, which I have written, contains all of the existing functions in the whole world. You cannot create those are continuous, but basically the whole idea is that you cannot create a function that is somewhere here that doesn't belong to this cube. It must essentially be in this cube. And by dense in this cube, I mean that we can get to any existing function, because if there is a tiny spot, yeah, like that, and we cannot get to it, we cannot represent it, we cannot approximate it as close as we want, then our blue space combinations, whatever, is not dense. But if we have a sigmoidal combination like that, and then it's dense, so we can get to any existing function, we can get as close to it as we want. Essentially, we can just almost, we can get as close to this thing as we want, and this what means it's dense, so we can represent everything in the whole world. Yeah, so that's it. A little eccentric, but whatever. This case is discussed in the most detail, but we state general conditions of other possible sigmoids. I'm gonna call it sigmoids. I just don't know what this letter is. Let's essentially know that. Oh, I'm sorry. Sigmoid function. What letter? Letter is used for it. It's called sigma. Yeah, I'm sorry, I'm so dumb. It's sigma. So all of the sigmas that we guarantee similar results. It's a bit related, like if you're reading it for the first time. I'm reading it, as I've stated, the second time, but the first time I wasn't actually deep enough to understand everything. We're stating that not only sigmoids can actually give us the properties of the denseness that we were talking about, there are other functions that are essentially used in neural networks right now, because sigmoids are not extremely good. The possible use of artificial neural networks in signal processing and control applications has generated possible, they're hype. Loosely speaking, an artificial neural network is formed from compositions and superpositions of a single, simple, nonlinear, or what? I missed it. Artificial neural network is formed from compositions and superpositions of a single, simple, nonlinear function or response function. About nonlinear function, everything is correct. We were talking about it for a lot of time. Just our sigmoid, just treat it as sigmoid, but I don't know what is a response function. I'm sorry. What is a response function? It's a mathematical physical engineering concept that describes how a system device in math. Function that describes how a system's output changes with the relation. Again, just a function. Just a function which has input and an output, as I understand that. So we have a kind of a response to the input. Accordingly, the output of the neural network is the value of the function that results from the particular composition and superposition of nonlinear. Again, this guy is stating the same thing like a million times, but I like it. Like, I cannot judge this guy. He's genius, I think. In particular, the simplest non-trivial class of networks are those with one internal layer, and they implement the class function given by one. So they are one layer. Just as we were talking about, we only have a weighted sum, a superposition of sigmoids, and they are represented just by the first thing, by this one. In applications such as pattern classification, is actually CNNs. Those are not neural networks, but again, if you understand the idea of how neural networks work, everything that is related to these transformers, I don't know, CNNs, you don't care about them, you just understand them intuitively, I mean. A pattern and nonlinear prediction of time series, for example, the goal is to select compositions and superpositions appropriately so that desired network responses meant to implement a classifying in nonlinear predictions are achieved. So it's just stating that, this theorem is related to neural networks, to prediction, pattern recognition, whatever we want to talk about. This leads to the problem of identifying the classes of functions that can be efficiently realized by artificial neural networks. This leads to the problem of the classes of functions that can be. So this touches the problem of what function can we use for the neural network. And in this theorem, as I know, we're gonna prove that, as I was talking about 5x, 6x, they're not gonna just work for a neural network. Similar problems are quite familiar and well studied in circuit theory and filter design, where simple nonlinear devices are used to synthesize and approximate desired transfer functions. Yeah, so those like similar things are used somewhere. We don't care about that. We care about the theorem itself. Thus, for example, a fundamental result in digital signal processing is the fact that digital filters made from unit delays and constant multipliers can approximate any continuous transfer. Yeah, so again, it's related to CNNs, just as I've been talking about it a lot. CNN is kind of a neural network that is used to recognize patterns, and it does it essentially by filtering some tiny fractures of the image. And sorry. And digital filters that are existing, those are which are not CNNs, they use the similar thing. They approximate any continuous existing function, essentially. In this sense, the main result of this paper demonstrates that networks with only one internal layer and arbitrary continuous sigmoidal nonlinearity enjoy the same kind of universality. Yeah, so again, we can do whatever we want with neural networks. We can approximate everything from recognition patterns, which they not just neural networks are capable of it, not just inefficient. So we can use a neural network as the solution to all of the existing problems where we can classify them as functions. Yeah. Requiring that finite linear combinations such as one exactly represent a given continuous function is asking for too much. Yeah, so we cannot represent them exactly. Understandable. In a well-known resolution of Hilbert's 13th problem, Kolmogorov showed that all continuous functions of n variables have an exact representation in terms of finite superpositions and compositions of small number of functions of one variable. Yeah, so there is a guy who has proven that using... Yeah, I'm just writing the next sentence. However, this guy's representation involves different nonlinear functions. The issue of the exact representability has been further explored in the context of projection pursuit methods for statistical data analysis. I think it's not really complicated, but I'm gonna break it down. Is that there is a guy who has proven that we can represent any function exactly. But the problem with his work is that he used different nonlinear functions. And obviously when we can find a superposition of one nonlinear function, it's gonna be impossible for us to understand all of the nonlinear fancy functions existing that are used to represent a certain function. It's not typically worth it, as we can approximate it really close. The issue of that, data analysis, whatever. Our interest is in finite linear combinations involving the same unvariate function. Yeah, so we're using the sigmoid or whatever, the sigma function. Moreover, we settle for approximations as opposed to exact representations. So if they are not exact representation, it is easy to see that in this slide merely generalizes approximations by finite Fourier series. Fourier series is it's complicated to break down. Yeah, it's gonna look like that. So Fourier series is essentially the same thing, is that we can use this fancy expression to represent a function, to represent any existing function. So we're just doing something related to Fourier series of x. The mathematical tools for demonstrating such completeness properties typically fall into two categories: those that involve algebras of functions leading blah 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 blah, and those that involve translation and variant subspaces. So those are two main big kinds of two different fields of algebra, complicated ones that we don't want to talk about, but though they adapt different solutions to the problem. We give examples of each of these cases in this paper. Whatever. Our main result settles a long-standing question about the exact class of decision regions that continuous valued single hidden neural network can implement. Some recent discussions of these questions are in contains one of the early rigorous analyses in Nissan showed that any set of endpoints can be into arbitrary subset by a network with one internal layer. So yeah, we're just talking that there are different people who implemented that. It's discussed somewhere. It's not really related to the proof itself. There has been growing evidence through examples and special cases that such neural network can implement more general decision regions, but a general theory has been missing, and made a detailed geometric analysis of some of the decision regions that can be construed exactly with a single layer. By contrast, our work here shows that any collection of compact disjoint subsets of n dimensions can be discriminated with arbitrary precision. That result is contained in theorem 3 and subsequent discussion below. Yeah, so he's stating that his work is cool, his work is decent, he can approximate everything with an arbitrary precision. By arbitrary precision, we mean that there must be a precision, but it may be as slow or as big as we want it to be, but it's not zero. That's the thing. And there is a theorem 3 which discusses it, and the discussion below also does it. A number of other current works are devoted to the same kinds of questions addressed in this paper. In monotonic sigmoidal functions in neural network with single layers are complete in the space of continuous functions. Yeah, that's it. That's what we were talking about. There is a guy called Hornig. He did the same thing. He has actually essentially proved it. Carl and Dickinson showed that the completeness property can be demonstrated constructively by using create and transform ideas. Cool, we can demonstrate it. Jones outlined a simple demonstration, criteria, given a demonstration. To be honest, yeah, like 2 hidden layers. He has proved it for 2 hidden layers, but now he's proving it to 1 hidden layer. Alright, so he's just stating that there are other guys who did the same thing. Not essentially the same, but the similar one. The main techniques that we use are drawn from standard functional analysis. Yeah, we're gonna dive in like functional analysis. It's not really interesting, but it's worth it, I swear to God. The proof of the main theorem goes as follows. We start by noting that finite summations of the form determine a subspace in the space of all continuous functions of the unit hypercube of n dimensions. So he is essentially firstly stating that they finite summations of the network, the combination of sigmoids, determine a subspace, so they have a certain subspace in our cube. So firstly he discusses that my cube is a little bit messy. Yeah, so first he says that they have their certain subspace. We don't know how big that is because it's maybe like that, but just a tiny subspace. Yeah. Theorem that subspace is annihilated by a finite that is big, that is essential of the cube. Must also annihilate every term, and this leads to the necessary conditions of sigmoids. So what he's basically doing here is that he is defining that sigma must have some conditions to be annihilated to all of the cube. All the basic functional analysis can be found in those papers. The organization of this paper is as follows. In section 2 we deal with preliminaries, state and prove the major result of the paper. So the whole, 90% of it is proven in section 2. Most of technical details of this paper are in section 2. In section 3 we specialize it to the case of interest of neural network theory and develop the consequences. Essentially we all know all of the consequences. We've stated the general problem, but it's worth reading, so our main focus is in section 2. Section 4 is a discussion of other type of functions, sigmas that lead to similar results. In section 5 is a discussion and summary. So essentially, just what I want you to understand from this video is everything that is down. The main part is here, the main results. It's It's not really big, it's just a few pages, but it's worth working on. I think I see a lot of math here. What we've stated right now is the introduction, that we understand the problem, we understand that this problem is wide, we understand how essential this problem is. The paper doesn't actually state that, but we can infer. And we are ready to dive into the main results. I think we're gonna do it in the next video. I'm gonna break those videos by the sections, because yeah, the second one is gonna be dull. Yeah, I'm ready. Alright, so thank you for watching. Hope you watch the next one if you're interested.